Welcome to Maths with Bob. Today we're looking at surds and what we can do with them. Well, the first thing is actually, what is a surd? Well, let's have a quick look. The square root of 2 is a surd, okay? How about the square root of 3? Yeah, that's a surd. Okay, how about the square root of 4? Now, okay, the square root of 4, okay, can be rationalized, okay? Although I can write it as an irrational form here, it can actually be rationalized. So we actually say that if a square root number can be realized or rationalized or turned into a whole number, then it's not a surd anymore, okay? Surds are actually square root numbers, okay? They are irrational by nature, and we can actually add them and subtract them and multiply them and divide them, but we can only add them and subtract them if they are like surds. So that's the first thing, okay, I think you need to work out. Okay, so we can we only add and subtract like surds. Okay. Okay. Now, the question is, what is a like surd? Okay. Well, is the square root of 2 the same as the square root of 3? Or are they like? No, the square root of 2 and the square root of 3 are not like surds. Okay, we need the number under the square root sign to be the same before they are like. So let's have a look. Is 2 lots of the square root of 2 like to 3 lots of the square root of 2? Can we add those? Yes, we could add those. Okay, we could get 5 lots of the square root of 2. So in a lot of ways, surds add and subtract it a little bit like algebra, okay, as long as the letters are the same or the letter combinations, remember, in algebra are the same, we can add and subtract them. So in algebra we can say we can only add and subtract like terms, but with surds we can only add and subtract like surds. Okay, now let's have a look. Okay, what happens when I go 3 root 5? Okay, what does this mean? Well, it just means the same as in algebra. That 3 at the front means there's 3 lots of root 5, so you could say that that's basically equal to what? The square root of 5 plus the square root of 5 plus the square root of 5. Okay, so there's 3 lots of them. Okay, so we can amalgamate them and just say that there's 3 of them. Okay, so first up we need to know that in fact the number at the front of a surd, we can actually bring it underneath. So how would we bring that number? There's a few tricks. We can actually say, well, 3 is actually the square root of 9. That's times the square root of 5. And we can actually say that that's equal to the square root of 9 5s, so 45. This is actually one of the surd laws. So we can actually bring those numbers at the front of surds back underneath the square root sign if we need to. But normally we don't. We normally take them out or try and simplify surds. Okay. So let's look at a few examples in simplifying surds. Okay, well, here we have a few quick examples before we start multiplying and dividing. Let's actually just have a quick look at a few additions and subtractions. Here, I'd like to just have a go at these. Okay, 5 root 7 plus 3 root 7 is 8 root 7 minus 4. Hopefully we can get, that's 4 lots of root 7. Okay, how about this one? Hold on, something's amiss here. These are different surds, so we can't do anything with these, so we just rewrite that as 2 root 3 plus 3 root 2. Okay, we can't add those, okay? They're not like surds. In the example 3, you can see here that some of them are like, so we can say 10 and 5, so 15 root 10. Okay, we can't do much with the 7 root 2 on the end. Okay. Now, you can also work with fractions. You can see here we have 1 half and a third is about 5 sixths, so it's basically 5 sixths minus a quarter, lots of root 3, okay, which would be what? 20 minus 6, okay, 14 on 24, so, okay, that'd be what, 14 on 24, lots of root 3. You can see here we go, what, 7 on 12, so it's about basically 7/12 of root 3. So we can actually take fractions of surds as well. Okay, so let's actually go into the multiplication and let's have a look at these. These are some of the main surd laws here. The square root of a times the square root of b is the square root of ab, which you can use backwards and forwards. Sometimes we use that one to simplify surds. We have the square root of a over b is equal to the square root of a over the square root of b, and the last one there, the square root of a all squared, is just back to a. Okay, so let's do some examples. Okay, let's have a look at the first one. Is the square root of 2 times the square root of 5? Okay, that is the square root of 5 2s are 10. How about if I put numbers at the front? Say I had 3 square root 7 times 4, say square root 5. Okay, we multiply the numbers at the front. 3 4s are 12. Square root, multiply the numbers under the square root signs. 5 7s, 35. Okay, how about I have letters at the front? A root 2 times 3a root 3. Okay, well we still can do this. We can go a times 3a is actually 3a squared. Square root of 2 3s are 6. Okay, how about if I had 2 1/3 root 5 times 1 1/4 root 7. Okay, well we need to multiply. Okay, let's have a quick look how we do this. 3 2 6, so it's 7 on 3 times 4 5 on 4. Lots of the square root of 5 7s are 35. Can we actually do too much with that? Not really. So it's 5 7s are what? 35 on 3 4s are 12. Square root 35. Now, interestingly enough, I can actually bring that 35 back in if I wanted to, but I'll just leave it as it stands. Okay, so let's look at some further examples on using these ideas. Okay, well let's do some more examples before we go on. Okay, what is the, say, the square root of, say, the square root of 25 on the square root of, say, 5. Okay, well we can actually use that one. We can just bring those together. Square root of 25 over 5, which is actually the same as the square root of 5. What happens if there are numbers at the front? Say, let's say 12 root, say, 36 on, say, 4 root 3. Okay, well, we can just say, okay, well, 12 divided by 4 is 3, so the number at the front will be 3. What goes underneath will be square root of, actually, what's 12? 3 into 36, 12. Now, we can see we can actually break this down. This is one of the things we're going to be doing next, is we can actually say, well, 12 is actually 3 times 4, so it's the square root of 4 times the square root of 3. And we can actually, square root of 4 is 2, so 3 2s are 6, lots of the square root of 3. This is one of the operations we do a lot with surds. We actually simplify them and try and add them. Okay. Okay, let's go ahead and do some further examples. First up, root 18. Hopefully you can see that's actually the square root of 9 times 2 minus the square root, well, break it up into a square rootable number. Okay, a perfect square, some people say. Okay, so we can see that that's equal to the square root of 9 times the square root of 2, which is really equal to what? 3 root 2 minus, now you end up getting 5 root 2 here. So the answer is actually minus 2 root 2. Okay, minus 2 root 2. The square root sign's a bit wonky. Okay, how about the next one? Well, 8 we can hopefully recognize is actually the square root of 4 times, I'll just write the square root of 2 minus 3 lots of the square root of 2. So the square root of 4 is 2, so 5 2s are 10, so that's really, what's that? That's really 10 lots of root 2 minus 3 lots of root 2, which is, see here, 7 lots of root 2. Okay, the next one, okay, 80. Well, 80 is actually, what's that, 16 5, so it's 3 lots of the square root of 16 times the square root of 5, plus 4 lots of the, now, that's 25 times 5, 125, so it's 25. I'll just break this up in a minute. Now, minus 3 lots of the square root of 12, which is 4 times 3. Now, okay, so let's have a quick look at this. Square root of 16 is 4, 3 4s are 12, so that's 12 root 5, that's okay. Square root of 25 is 5, 5 4s are 20, okay, so it's 20 root 5. Okay, minus the square root of 4 is 2, 3 2s are 6 root 3. Now, you can see here we've got unlike surds, but we can actually, some of them are like, so we can actually add them together. What's that, 32 root 5 minus 6 root 3. Okay, the last one, this set of examples, we can see that, well, the square root of 9 is 3, so this is really what, 15 root y. Now minus the square root of 4 is 2, 4 2s are 8 root y, okay, and hopefully we can see here that that's just 7 lots of root y. Okay, All right. Okay, you can see here we've got a few more examples with brackets, and they work a bit like with algebra. I just remember this one goes this way here and across to there. So we actually multiply the first time by both the terms on the inside of the brackets. It's just like normal algebra expanding brackets, but we're just dealing with surds. So let's go through and work these out. Okay, so the first one is root 5 times 2 root 3. So it's actually 1 root 5 times 2 root 3. So 1 times 2 is actually 2, and root 3 times 5 is root 15. Now we have a minus 5 times a root 5, minus 5 lots of root 5. Well, that was a nice easy one. Now the next one, how about, let's have a quick look. Well, we can see here 4 2s are 8. Hopefully we've got 4 root 3 times 2 root 6. We multiply the numbers together on the outside of the square root signs. 4 times 2 is 4 2s are 8. And we multiply the numbers underneath the square root signs together as well, and put them underneath the square root sign. So it's 3 6s are 18. Now we'll be able to simplify this, which I'll do shortly. Then the next term, let's have a look, going to be a minus or a negative term, because we've got minus 3 lots of root 3 times a 4 root 3 at the front there, so it's going to be 4 3s are 12, okay. Okay, now we have a square root 3 times a square root 3. You might remember this from one of the surd laws, isn't that actually the square root of 3 times the square root of 3, or a surd times itself is actually the number underneath the square root sign, which in this case is just 3. So it becomes like 3 times 12 on the end here, which is just 36. Okay, we'll just simplify this one. We have 8, now root 18, 9 times 2 if you like. Okay, minus 3 12 is 36. And the square root of 9 times 2, can be broken up into the square root of 9 times the square root of 2, and the square root of 9 is 3. So it becomes, this becomes what, 8 3s, 3 8s are 24, and there's still a root 2 there, and minus 36. Okay, so we've eliminated the brackets. Okay, so let's have a look at the next one, part C. Now root 5 minus root 2 all squared. Well, let's just use the identity, which is, you might remember, a squared minus 2ab plus b squared. That's the identity. And let's just apply it now to the surds, where a is actually, obviously, a is root 5 and b is root 2. So a squared, obviously, is root 5 all squared, which is just 5, minus 2 times root a times root b. Well, I should say 5 times, the square root of 5 times the square root of 2, I should say here. So it's, what's that, 2 lots of root 10, 5 2s are 10, root 10. Okay, and the number on the end would be, okay, root 2 all squared, just a 2. So this just works out to be what, 7 minus 2 root 10. Okay, let's try the other one, the last one here. Now, you can see here a is actually the whole expression, and this is, okay, this would be what? We're using the a squared now plus 2ab plus b squared, because it's really like a squared plus b squared, and the a is actually 2 root 3. Now this is getting an interesting one, so let's actually write this out. We need to probably, we get 2 root 3 all squared plus 2 lots of, now it's 2 root 3 times 4 root 2, and then it's going to be plus 4 root 2 all squared. Okay, so now 2 root 3 all squared, well that's 2 root 3 times 2 root 3, which is 4 lots of 3, which is 12. Okay, so the first number is 12. You might like to try that, verify that yourself. 2 root 3 times 2 root 3 is 2 2s are 4. Root 3 times root 3 is 3, so it's 4 3s are 12. Now let's have a look at the next one. 2 times 2 is 4. 4 4s are 16. So it's actually 16 lots of root 2 3s are 6. And the last term here will be what? 4 root 2 times 4 root 2, which is 16 times 2, which is 32. Okay. And we can normally just add the numbers together. You can see here will give us what? What's that? 44 plus 16 lots of root 6. Okay, well now we'll just move on to the last little section called rationalizing the denominators. Okay, we're now going to rationalize some denominators. Now, First of all, what is the denominator? Well, that's the bottom part of the fraction. Remember, the top's the numerator and the bottom's the denominator. And normally, I'll just show you an example of one. Say we had 2 over root 3. Okay, now this is a fraction with an irrational denominator. And you can imagine getting a cake or something and trying to divide it, instead of into thirds, to make it into sections of root 3 in size. It's slightly difficult. And this is one of the reasons why we do what's called rationalise the denominators. Okay, so we have this idea of a fraction being two rational numbers normally, and we would normally have a rational number in the denominator. Okay, so what are we going to do? Well, the first thing we'd do is, let's actually, the easiest way is to use this fact, okay, that if I multiply a surd by a surd, it becomes a rational number, okay, and then we end up with, what, 2 root 3 over just ordinary old 3. So we now have a fraction. Well, it's technically still irrational, because it has, as you can see, irrational in the numerator, but it's considered better than having an irrational number in the denominator. Okay, so we normally, what we'll do with these sorts of fractions, if you like, or irrational numbers with surds or irrational expressions in the denominators, is we actually what's called rationalise the denominators, okay, by a couple of tricks. This is one of the first tricks, and you'll see here multiply by the conjugates is another one. Okay, so let's do another example. Suppose we had 2 root 5 over 3 root 7. Okay, how are we going to do this one? Well, you can see the easiest way would just be multiplied by root 7 over root 7. I mean, we don't need to multiply by 3 root 7 over 3 root 7, just multiply by root 7 over root 7, because you can see here that would give us what? 2 lots of root 7 times 5 is root 5 7s are 35 on the top, and you can see here on the bottom I get 3 times root 7 times root 7, which is just 7. 3 7s are 21. Now I have a rational denominator. Okay, the numerator is still irrational. Okay, so let's actually have a look at a few further examples where we need to be a bit trickier. So let's actually just rub these out. Okay, so first step is, what happens when we have something like this? Okay, say 2 over 3 plus root 5. Okay, in these sorts of problems, we multiply by the conjugate, which is 3 minus root 5 over 3 minus root 5. Now, that's just like multiplying it by 1. If you like, it's a bit of a manipulation, if you like, so that in fact the denominator becomes rational. And you can see here we have really, if you have a look here, we really have what? A plus b times a minus b. Okay, so we have this thing here called the difference of two squares, which is a squared minus b squared. And obviously, if they're surds, if a and b are both surds, then that would turn into a rational number. So we just go ahead and do this one now. Okay, so we'll get 2 lots of, let's have a look. 2 times 3 is 6 minus 2 root 5. Now, what does the bottom work out to be? Well, it's 3 squared minus root 5 all squared. Okay, and as we wanted, we end up getting what? 6 minus 2 root 5 on 9 minus 5, which is actually 4 on the bottom, and has we can cancel a common factor of 2. So if that was 4, you can see here we actually be able to, 2 lots of 3 minus root 5 on 4, we can see here 2. So we can actually simplify that to be what? Root 3 minus root 5, just all over 2. Okay. All right, so let's do another example. Okay, let's just rub this out. Okay, let's make it a bit more interesting. Okay, suppose we had 5 plus 2 root 3 over, say, 2 root 5 minus 3 root 2. Okay, how are we going to rationalise the denominator in this case? Well, again, we just multiply by the conjugate, which is just really 2 root 5, okay, plus 3 root 2. The same as the denominator, but with an opposite sign in between, you could say. Okay, so it's 2 root 5 now well, obviously this is a plus 3 here, but you can see we're using the difference of two squares idea to realize, if you like, or rationalize the denominator in this case. Okay, so again, we'd have, okay, we're going to have to multiply this out, so let's have a look. Okay, let's just quickly do it, okay, so we have 5 times this would be what, then 5 times this one, then this one times this one, and this one times this one, so let's actually just do that now. Okay, so 5 2's are 10 root 5 plus 5 3's are 15 root 2, and this is still in the numerator. Then we have a plus 2 2's are 4 root 3 5's are 15, and a plus in the end here, 2 3's are 6 lots of root 6. Okay, we can't do much with that numerator there, or unlike surds. Now, however, on the bottom we can actually, let's have a quick look. We have 2 root, let's actually just write it out. We have 2 root 5 basically squared minus 3 root 2 all squared, and that would be, what's that? 2 squareds 4, 4 5's are 20, minus 3 squareds are 9, twice 9 are 18. Okay, so the bottom turns out to be just 2. Can we divide everything by 2? Not really, but let's just try 5 lots of root 5 plus, now let's write this 15 on 2, or 7.5 lots of root 2. I just write this 15 on 2 root 2. Okay, half of 4 root 15 is just 2 root 15, and half of 6 root 6 is 3 root 6. Okay, so the bottom was actually 2. So we're just halving the numerator now. Okay, so this is our final answer down here. Okay, so you can see you can do all sorts of other sorts of problems. We'll just do one final one. Okay, you can see here this is a typical sort of question. Let x equal 2 minus root 3 and evaluate 1 on x plus x, or it could be 1 on x squared plus x squared, or sort of combinations of these ideas. So first of all, let's go through and do it. Well, okay, 1 on x, we now have 1 over 2 minus root 3, and then you have to multiply that by 2 plus root 3 over 2 plus root 3. And then you still have the x on the end, which is actually just 2 minus root 3. Okay, so let's quickly go through and work out what happened here. We end up getting what? 2 plus root 3 all over 2 squared, which is 4 minus 3. Okay, that's nice. Okay, plus 2 minus root 3. You can see here this one simplified nicely because the actual denominator over here is actually 1. So that's 2 plus root 3 plus 2 minus root 3, which is just 4. I mean, they don't always work out this nicely, but just made that one up. It seemed to work out very well. So, but sometimes you may need to add the other parts. Okay, well, we'll just leave it for today, and thank you for watching.